Hello students, welcome to Pi Academy, the place for mathematics and science. Dear students, in today's class we are going to continue the chapter Magnetic Effects of Electric Current. And remember, this is 5th period of this chapter. And in 4th period we learned some of the important concepts along with the activities. Just we shall go for recalling these one after the other. In the very first activity, see that a conductor carrying current is kept in the magnetic field. What happens? Yes, it experiences the mechanical force, right? That means here whatever the magnetic field is there around this horseshoe magnet will exert the force on this conductor in which current is flowing. Then how did you come to know the direction of mechanical force acting? Yes, it was understood by using Fleming's left-hand rule. Then what is the statement of this? Yes, according to this, arrange the first three fingers of left hand mutually perpendicular to each other, right? If the forefinger indicates the direction of the magnetic field and the middle finger indicates the direction of flow of current, then the thumb indicates the mechanical force acting. Please do remember this. And this Fleming left-hand rule is also known as motor rule. Because here we know that the electric motor, it is a device which converts electrical energy into mechanical energy. Here also, see that here current is passed through the conductor and it is kept under the influence of the magnetic field of the horseshoe magnet. Then it exerts the force. The mechanical energy will start acting on it. So for this purpose, that is converting electrical energy into mechanical energy, we go for using the device that is called motor. Hence Fleming's left-hand rule is also known as motor rule. Then after that we checked whether the reverse effect of this is possible. That means here that is magnetic field, whether magnetic field can produce electric field, nothing but electricity. Certainly it is possible, and it was answered by a great scientist, yes, Michael Faraday, through his experiment, and that experiment is familiarly known as Faraday's experiment. See, in that we know that here he will go for taking a cylindrical cardboard and it is to be winded with a long copper wire. Then the free ends are connected to terminals of a galvanometer to check whether the current is induced or not. Then after that he inserted the north pole of the bar magnet into the coil. Then immediately he noticed that the needle in the galvanometer deflected towards one side. That means current is produced in the coil. Then he pulled back the magnet from the coil. Again there was deflection in the galvanometer, but it was in the opposite direction. That will also indicate current is induced. Then when the magnet is kept inside the coil at rest, but there was no deflection, which indicates no current is induced. So what is the reason for not inducing the current? The reason is when the magnet is kept inside the coil, whatever the magnetic field around the magnet, it does not change at all. It is completely ceased. So that is why no current is induced. But when the magnet is either inserted or when it is pulled from the coil, current was induced. The reason is here the magnetic field get changed because these magnetic lines of force are cut by the turnings. Clear? Hence we can say that a changing magnetic field, please do remember, a changing magnetic field can induce the current. Then what did he call this phenomenon? It is electromagnetic induction. How do you define this? Let's go for defining. It is whenever the magnetic field linking with the coil changes, then the current is induced in the coil. This phenomenon is known as electromagnetic induction. And here, whatever the current is induced, it is called induced current. And this phenomenon was discovered by Michael Faraday. Please do remember that. And there is a device which works on electromagnetic induction, that is dynamo. Dynamo is a device which converts mechanical energy into electrical energy. We will get very good information about dynamo and motor in today's class only with diagram and construction. Okay, here whatever the current is induced, this direction of induced current was explained by again the great scientist E.S. Fleming through his rule called Fleming's right hand rule, and this is also known as dynamo rule. Dynamo rule, and it is also known as generator rule. Then what is the statement of this rule? Here, according to this rule, arrange the first three fingers of right hand mutually perpendicular to each other. If the forefinger indicates the direction of magnetic field and the thumb indicates the direction of motion of the conductor or coil, then the middle finger indicates the direction of induced current. Clear up? Yes. Here, whatever the current is induced, this current depends on some of the factors. Induced current depends on some of the factors. Then what are these factors? Just we shall go for recalling one by one. First one is the speed of the magnet. As the speed of the magnet increases, induced current also increases. How? As the speed increases, the lines of force cut faster. Due to this, field get changed faster. Clear? Another factor is the strength of the magnetic field. As strength increases, that means the amount of magnetic field increases, then again current induced also increases because more amount of field get changed. And third important point, the number of turnings of the coil. As the number of turnings increases, field strength, the change in the field also increases. Due to this, induced current also increases. Clear? So this much was learned in the last class. Now we are moving to the next part of this chapter. Dear students, now we are moving to another important activity. No need to go through this statement. Just observe the figure only. Here I have taken two coils. You may go for calling first one as coil 1 and you may also call it as primary coil. And this is coil 2 and you may call it as secondary coil. Just keep observing these two. In the first coil, the free ends are connected to terminals of a battery along with the switch. Whereas second coil, the free ends are connected to terminals of a galvanometer which is used for checking whether the current is present or not. Right? Look here, and these two coils are inserted. A cylindrical cardboard is inserted into these coils. Now, could you tell what happens when I close the circuit of the first coil? Yes, the current starts flowing from positive terminal to negative terminal, right? Then we know that whenever the current flows through the conductor, the magnetic field is developed around it, which is nothing but magnetic effect of electric current. Then when the current is flowing in this, do you find any change in the second coil? Yes. As soon as the current flows, here also, here the current is induced. Why? That can be known by observing the deflection of the needle in the galvanometer. The reason is, here the coil is there. When the when you pass electric current through the first coil, whatever the magnetic field is developed, under this field, this coil will be present. And as the field get changed, so then the magnetic field linking with the coil changes, the current is induced in this coil. Similarly, when the switch off, immediately again you can come to know that this time the needle in the galvanometer shows the opposite direction, then finally come to rest. Clear? Please do remember, when all of a sudden the current is passed in the first coil, then current is induced in the second coil. When it is removed, again the current is induced in this coil, but it will be in the opposite direction. Clear? When no current is flowing in the first coil, here also no current is induced. Understood? So from this we can conclude that the current is induced in a coil when the current in the neighboring coil changes. Clear? When all of a sudden current flows, when all of a sudden circuit is broken. In both the cases, current is induced in the coil because it will be under the influence of magnetic field produced from this coil, coil 1. Followed? Now please go for writing the statement to demonstrate that the current is induced in a coil when the current in the neighboring coil changes. Please copy this. Yes. Please go for writing the procedure. Just what I have explained in the same way I have written. First we take two coils, and the first coil is connected to terminals of a battery along with the switch, and second coil is connected to the terminals of galvanometer. Then you will go for taking a long cylindrical cardboard, and it is to be inserted into the coils. Then after that, when you switch on in the first coil, then the current flows, then magnetic field is developed around it. Then as soon as on observing the galvanometer, you can come to know that there is deflection in the needle. That means current is induced in the second coil, and immediately it comes to 0. That indicates the current induced will be momentarily, that is for temporary only. Then after that, when you switch off this first circuit, that means when you breaks the circuit, then also there will be deflection in the needle of galvanometer, but it will be in the opposite direction, which means current is induced in the second coil in the opposite direction. In both the cases, current is induced momentarily. It is because of the change in the magnetic field linking with the coil. Clear? That only has been written. Please go for writing from here to here. Then after that, copy these points also up to here. Go for copy. Dear students, in this chapter, we are going to learn detailed information about two important devices which work on based on what we learned so far. One is magnetic effect of electric current, and second one is electromagnetic induction. They are dynamo and motor. Dynamo works on EMI, motor works on magnetic effect of electric current. Okay. Here, with respect to these two, first we will go for defining it, then we will write the principle on which it works, then diagram, construction, working, and some terms related to that. Okay? Yes. Now, we will learn one by one. In that, the very first one is, it is dynamo. Dynamo is also called electric generator or simply generator. Then what is dynamo? Dynamo is a device which converts mechanical energy into electrical energy. Please do remember. Here I will write the device which converts mechanical energy into electrical energy. Mechanical energy into electrical energy. Electrical energy is called is called dynamo. And this dynamo, it was discovered by Michael Faraday. It was discovered by Michael Faraday. And this works on the principle that electromagnetic induction, EMI. Then even they may ask you to write the statement of the principle on which dynamo works. You have to write a changing magnetic field linking with a coil induces the current in the coil, or when the magnetic field linking with the coil changes, then the current is induced in the coil. I'll go for writing the statement. It is whenever the magnetic field linking with the coil changes, then the current is produced or induced in the coil. This is the principle. Now, I'll go for drawing the diagram of dynamo. It can be given in the examination. That is, draw a neat level diagram of dynamo and explain its working. This is the question was asked in the previous year question papers as well. Now I am going to draw that. Please go for writing from here to here. Right from here to here. Dear students, here observe, I have drawn the two-dimensional figure of dynamo or generator. Look here. First I will go for explaining the terms. Here N and S, these are the poles of a magnet, poles of a field magnet. Here we go for using U-shaped magnet as field magnet, nothing but horseshoe magnet. It will be like this. Got it? In this way. See that? North pole and south pole. And in between we have placed a rectangular coil of insulated copper wire, which is ABCD. See that? ABCD. It is a rectangular coil of insulated copper wire. That is, it is placed in this way. It is a horseshoe magnet and we have placed the rectangular coil in this way. ABCD is a rectangular coil of insulated copper wire and it is placed between north and south pole of field magnet. Clear? Then the free ends of the copper coil is connected to two rings, copper rings, and these rings are full rings. Rings means obviously it will be like this, right? Look here. It is copper ring and there are two such copper rings are used and which are in contact with B1 and B2. B1 and B2 are the carbon brushes. Nothing but they will not be having brushes, but they are carbon plates. They are the solid substance, like a brake rubber which is attached in the wheels of a bicycle. You might have observed that. It is just like B1 and B2 are the carbon plates, also called carbon brushes. And here these two are connected to terminals of a galvanometer, because we know that dynamo is a device which converts mechanical energy into electrical energy. So we should come to know whether the current is induced or not. Then W, it is the wire, that is nothing but copper wire which we use to connect to B1 and B2 along with the galvanometer. Next, here we have used the shaft with handle, nothing but axle. The reason is to make the rectangular coil to rotate, right? Why should we rotate? The reason is here whatever the magnetic field is present between north and south pole of the magnet, it should be changed. To change that, we will go for using by rotating. Look here, by rotating the coil, these lines of force are cut. When they cut, the magnetic field changes. When the magnetic field changes, current is induced. That induced current can be seen here. Even you may go for using an LED bulb also, because you can come to know that when the bulb glows, you can decide that current is induced. Clear up? Yes, these are the terms. Once I repeat, N and S are the poles of field magnet, nothing but U-shaped magnet. ABCD is a rectangular coil of insulated copper wire. Third one, R1 and R2 are the copper rings, full rings. They are also called slip rings, SLIP, slip rings. Then B1 and B2 are carbon brushes. G is galvanometer, W is the wire, and it is shaft, nothing but axle. Then construction. Construction is very simple. See that ABCD is a rectangular coil which is rectangular coil of insulated copper wire mounted between poles of field magnet. Then the free ends of the coil are connected to two copper rings R1 and R2, which are in contact with the two carbon brushes B1 and B2 respectively. That is, B1 is connected to R1 and B2 is connected to R2. Then connect the carbon brushes B1 and B2 to the terminals of the galvanometer, galvanometer. Then after that, fix a shaft to the coil to change the magnetic field. This is about construction. Working. Listen here. Current is induced if and only if the magnetic field linking with the coil changes, right? If the magnetic field has to be changed, so they have to be cut. How do you go for cutting? By rotating the coil using the shaft. See, here we have an axle with a handle. By rotating it, how do you go for rotating? I'll go for taking the clockwise. See, here I'll write clockwise direction. When this rectangular coil is there, it is also known as armature. When this armature is made to rotate in the clockwise direction, then magnetic field linking with this coil changes. Then the current is induced. Then what is the direction of current? This direction of current can be known by using Fleming's right hand rule, which is also called dynamo rule. Observe it. Now I am going to use the Fleming's right hand rule. See that lines of force spread from north to south. See that these are the lines of force, and these lines of force are cut by the coil. And what is the motion of the coil? It is clockwise, right? It is moving downward. You can observe that. Lines of force from north to south, and motion of the coil, it is downward. And where the current is induced? Current is induced through A, B, C, D. Clear? Then when the coil is made to rotate, half, then look here, this R1 comes in contact with B1, right? Then the current in the external circuit flows from B1 to B2. Hope that you have understood. Here, when the armature is made to rotate in the clockwise direction, then the magnetic field linking with the coil changes. Current is induced in the coil through A, B, C, D, and D comes in contact with B1, and current in the external circuit flows from B1 to B2. Clear? Hope that you have understood. Then again, when you continue to rotate the coil during the next half rotation, the current in the coil induces and flows through D, C, B, A, and A comes in contact with B2. Current in the external circuit flows from B2 to B1. I hope that you have understood. I'll go for showing how the current will pass in both the cases during first half rotation and